I'd like to welcome everybody here for a real treat for this breakfast morning. Thanks for getting up early, but I think we're going to have a really inspiring set of speakers here talking about something that couldn't be more current these days. I'm pleased to know these gentlemen for a few years going back, and I would say Fred needs no introduction, but I'm going to go ahead and do that anyway. He's done a lot of breakthrough work in integer programming, combinatorial optimization, and Taboo Search has his fingerprints all over it as well. Hundreds of papers published and awards, including the von Neumann Prize. But he's such a great gentleman and a great person and a great resource. So welcome you here, Fred. Thanks for getting up so early. And also Gary. Gary is an esteemed colleague and friend of mine who's also published widely in for combinatorial optimization. And they're going to talk about their ventures here on Quadratic, Unconstrained binary optimization. And their third author, Rick, can't be here, but in the slides he's there, and in the content as well. I'm going to now turn it over first to Fred.
Thank you very much, Doug. And a special thanks to Doug for hosting this for us. And a welcome to all of you, courageous and enterprising folks who made it out this morning, early at 8 a.m. So I'm just going to kick it off for the first few slides, and then Gary's going to take up the main part of it here. Here we go. So, as this says, recent years, there's been a lot of excitement about quantum computing, of course. And some of that excitement has been really hype, I must admit, from the quantum computing community. But they have brought to our attention the relevance of this model for a large number of applications, starting with the physics community and the quantum computing groups, with the Ising spin glass problems. Now, in fact, the Ising spin glass problem had also been known for quite a number of years, but the quantum computing folks really picked up on it. And this model is called the QUBO model, which is a quadratic unconstrained binary programming model. Has an enormous number of applications. So what we're going to talk about is what is this model, how to construct it. If you guys want a primer in doing that, Gary's going to give you the details. How it's been used to address various problems, and we'll be talking about some combinatorial, some computational experience that I think you'll be really interested to see. And I might mention that we do have extensions beyond the QUBO model as well, and we're hoping that the rest of the quantum computing community will pick up on this. So now, an intro. This formulation is kind of an esoteric one, the X transpose QX, but just think of it as a quadratic problem. You have quantities, a sum of constant terms and regular variables, and then cross-product variables. And Gary's going to be giving you a number of illustrations of this. Now, here's why it's beginning to really catch on. It unifies a lot of models, surprising number of models in combinatorial optimization, and it's sort of the bulwark, the underpinning of investigations for quantum annealing computers, the IBM neuromorphic computers, the QAOA computers, and the Fujitsu digital annealer. All of these groups have been focusing a great deal on QUBO models. Now, some of them emphasize that they can do things beyond QUBO models, but the QUBO models have been really the primary focus of attention. Well, this just iterates what I've just said. This last comment, though, one model, one solution technique, that's not quite accurate. There's quite a few solution techniques out there, but as you'll see later on, they're not all as effective as one or two of them. And Gary will give you the scoop on that. This is a few of the groups, they're not nearly all of them, that are really chasing after these models. Google, Amazon, IBM, Lockheed Martin, Los Alamos National Laboratory, which Gary and I have a connection with, the Oak Ridge National Laboratory, Lawrence Livermore National Laboratory, and the NASA Ames Research Center. So you can see that this is catching on quite widely. And some of the applications that are really capturing attention too, financial services, especially portfolio optimization. It was a surprise to Gary and me how much is going on there. They're really digging into this. Transportation, manufacturing, pharmaceuticals, materials, and life sciences. We've been seeing RNA and DNA folding problems too that are coming into this area. Energy and utilities and so forth. And then those of you who have played around with some of these classical combinatorial optimization problems will recognize a lot of these names. And the QUBO models are very, I wouldn't say prominent in the sense of having eclipsed other things, but they are right in this, applicable to all of these areas. Coloring problems, capital budgeting, max independent set, maximum cut problems are a big one. Linear ordering, satisfiability, clustering problems. I've been surprised about how relevant it is to clustering, but this goes on. I'm going to turn this over to Gary now, and he's going to give you the fun part of this.
Thanks, Fred. And thanks, Doug, again, for organizing this. Before I move on from this slide, I want to just simply comment that most of you will recognize all of these as well-known combinatorial problems that academics work on and some people in industry are interested in. We've actually applied this QUBO model to all of these instances and all these categories with really great success. And we have papers on most of these areas with applications of QUBO in those particular areas. Okay. So what I'm going to do now is kind of give you a tutorial on how to build these QUBO models. And the basic idea is that you take a classically formulated model and you reformulate it as an unconstrained quadratic model by representing constraints as quadratic penalty functions. And I'm going to give you a lot of examples of how you might do that. And so the idea is to add these penalty functions to the objective function, kind of in the spirit of Lagrangian relaxation, that type of construct, but it's computationally quite different than that. But that's the idea. You represent constraints as penalties that are put into the objective function. Any polynomial model in binary variables, in principle, could be of a classical formulated problem could be recast into the form of a QUBO model. In most of the applications we look at, the traditionally formulated model starts out being a linear or a quadratic objective function in binary variables, typically subject to linear constraints. That's the typical setup that we get started with. Any problem of that nature can, in principle, be recast into the form of a QUBO model and solved as this unconstrained quadratic binary optimization problem. Now I'm going to take you through some very explicit examples of how we create these QUBO models, and there's 2 or 3 different categories that you might think about. So some optimization problems are just naturally QUBOs, and just straight away you get a QUBO formulation. Max cut is probably the most famous example of that. Number partitioning is another famous example of that. So if you have a max cut problem, you initially have a QUBO model. In most applications, though, we find a traditionally formulated model with constraints, explicit constraints, and we have to represent those constraints in the recasting into a QUBO model by these quadratic penalties. For some well-known but simple constraints, these quadratic penalties are known in advance, a priori, and you can simply stick them into the objective function. And I'm going to give you some examples of that in a moment. But for the more general case, for when you run into a traditionally formulated model for which you do not initially know a good quadratic penalty to use, there's a general purpose approach we're going to show you as well. And we use it all the time. It works quite nicely. And so I'm going to take you through these 3 categories where we have known formulations, that is to say natural QUBOs, where we build QUBOs, where we have knowledge a priori about what to use as a quadratic penalty function. And then I'll take you through some examples on the more general case. I might comment before I leave this slide, though, that there are special instances that arise for which special quadratic penalty functions can be constructed. And we ran into that, and we developed special penalties for the linear ordering problem, which is a very challenging combinatorial problem. I'm not going to go through that today, but we have a paper on that if anyone's interested in how we went about building a QUBO for that linear ordering application. Okay. So the first example I want to give you is just the max cut problem. I know everyone in this room knows about the max cut problem. We have an undirected graph, and we want to partition the vertex set into 2 sets such that the number of edges between the 2 sets is maximized. Okay? So we model that in a combinatorial sense by decision variables xj equals 1 if vertex j is in one set and xj is 0 if it's in the other set. Okay? And so if you look at this quantity xi plus xj minus 2 xi xj, if that quantity is equal to 0, that means that vertices I and j are in the same set. But if that quantity is equal to 1, that means they're in different sets. So you can simply build a model, a combinatorial optimization model, that finds the max cut by formulating that objective function as shown there in the middle of at the bottom of the slide there. And that, of course, is just a quadratic function in these decision variables xi and xj. So you can rewrite that, of course, in the form of the QUBO model as shown on the bottom of the slide there. Minimize x transpose qx, where q is just a symmetric matrix of constants. Okay? And that, of course, is the classic formulation, QUBO formulation, that Fred mentioned earlier. Okay? So here's a simple example of that, a little graph with 5 vertices and 6 edges. If you simply write out that quadratic objective function as shown there on the bottom of the slide, and of course you can rewrite that in the form of x transpose qx. And so this is what the Q matrix looks like for the QUBO model for this particular little example, and that model is very easy to solve, and you get that the max cut is equal to 5. Later on in the presentation, I'm going to show you some computational experience with max cut problems. We're solving them with up to 1 million variables now, so 1 million nodes, yeah, and using this very QUBO methodology. Okay. Well, most often you run into problems that have constraints, and as I mentioned a moment ago, for some very well-known but simple constraints, we know the quadratic penalty functions to use up front, okay? And when that happens, you simply identify the penalty function to use, stick it up into the objective function, and you generate your QUBO model, okay? So I want to show you a chart that has some standard well-known little constraints and their corresponding penalty functions. So, and we run into, actually, these simple little constraints appear in all kinds of important models, okay? The first one in particular, and by the way, all the variables on this slide are 0, 1 variables, so everything we're doing is binary here, okay? This is binary breakfast time, okay? Yeah. So this very first constraint, x plus y less than or equal to 1, that constraint, of course, says that not both x and y can be chosen at the same time, and that shows up in many, many really important applications. In fact, well, let me comment. If you go over to the right-hand side there, where we have the corresponding quadratic penalty, where p is a positive scalar, so p times the product xy. So if you take a look at that quadratic penalty there, and if you think about if you had a minimization problem, and you stuck that quadratic penalty up into the objective function, the optimizer you use is going to try and set x and y so that they're not both equal to 1. It's going to try and set that penalty function to 0. So it can say neither can be 1, one or the other can be 1, but it's going to avoid setting both of them equal to 1. And that's exactly what the constraint on the left-hand side, the classical constraint, says as well. Okay. So that's the idea. This little constraint, the first one on this chart, is so prominent in applications. Fred and I run into it all the time, and we refer to that, and I will later in this presentation as well, we refer to that as transformation number 2. Number 2. Number 1's yet to come. I don't want anyone to leave this presentation, so I'm giving you number 2 first to give you number 1 later on, okay? Likewise, the rest of the constraints on the left-hand side of this chart appear in lots of applications. And on the right-hand side, we list a corresponding quadratic penalty function that can be used in place of the traditional constraint on the left-hand side, okay? So let's see how we might use this chart to build a QUBO model for another well-known problem, the minimum vertex cover problem, widely known problem in combinatorial optimization. And again, this problem can be modeled as a combinatorial optimization problem by introducing binary variables. So xj is equal to 1 if vertex j is in the cover, otherwise it's equal to 0. So the standard, the traditional combinatorial optimization model for this minimum vertex cover problem is listed here on the slide. You simply minimize the sum of the x's subject to these constraints, xi plus xj greater than or equal to 1. And of course, those constraints say that not both xi and xj can be 0, okay? One or both can be equal to 1. And if you think about it for a moment, in a large graph, if you want to solve the minimum vertex cover problem for a large graph, you could have many, many constraints of this form, okay? Could be thousands and thousands of these constraints. To build our equivalent QUBO model, we're going to take each of those constraints, formulate them as quadratic penalty functions, stick those penalty functions up into the objective function, and we'll have our quadratic model, our QUBO model. So if we go back and look at our chart, we see that the second traditional constraint in our chart, x plus y greater than or equal to 1, we see on the right-hand side there a penalty we can use, a quadratic penalty that is 0 for feasibility on the left-hand side and positive for infeasibility, the infeasible case, yeah. So we know how to do this for the minimum vertex cover problem. We simply take this constraint, this quadratic penalty that's listed there, stick it in the objective function, and here we have a QUBO model. We'll have to rewrite this in the form of XQX, but this is, I wanted to show you the underlying construction, okay? Where again, P is a positive scalar. So here we have our quadratic function that we rewrite as XQX. Writing it as XQX, this is what the Q matrix looks like. And this gives me an opportunity to emphasize once again that the simple formulation X transpose QX, all of the problem data is folded into the Q matrix. It's a symmetric matrix, can always be formulated in a symmetric form. It's obviously easy to solve this tiny example, and you get the result that y is equal to 3 there. Another example that is widely known in the combinatorial optimization community, you know, the max set problems. We've worked on both max 2 set and same methodology can be applied with a couple little tweaks to the max 3 set problem. So if you think about the problem max 2 set, there are 3 possibilities for each literal or each clause in the problem. You could have no negations, you could have 1 negation, or you could have 2 negations. And for each of those cases, there's a traditional constraint. So for the example, for no negations, the constraint is simply xi plus xj greater than or equal to 1. And for that, we know from our chart there's a quadratic penalty function we can use. And likewise, for the second case where we have 1 negation, and for the third case when there's 2 negations, we have a quadratic penalty from our little chart that we can use. The point is that if you want to solve a max 2 set problem, all you have to do is take these quadratic penalties for each of the clauses in your problem, simply add them together, and you get a QUBO model. Several years ago, Fred and I and a couple other coworkers solved lots of max 2 set problems with hundreds and hundreds of variables, thousands of clauses, and the QUBO model delivered solutions very, very quickly. Okay. Again, we have a paper on that if anyone is interested. So some problems like max cut and number partitioning are naturally QUBO. Some other problems that have pretty simple constraints can be converted, recast into the form of a QUBO model using the penalties from the little chart that I gave you. But what the heck do you do if you have a problem and the constraints aren't on our chart? How do you go about that? Well, there's a general procedure that's pretty straightforward, very easy to use, in fact. So if you start with a general, traditionally formulated problem, as shown there, you know, max cx subject to ax equal to b, and again, all of these variables in this problem are binary, okay? So if you have this general formulation, you can construct a QUBO model as shown here on the slide. You simply add, in more general terms, the quadratic penalty for all of your constraints ax equal to b into the objective function. You simply clean up the algebra and you're left with the bottom line there that is x transpose qx plus an additive constant. You pick up an additive constant when you do this, okay? So you write a little Python code or whatever you want to use to do this. It's very easy to convert your constraints into quadratic penalties and generate your QUBO model as shown here. And this general, this transformation from a traditionally formulated problem to a QUBO, using this general approach is what we call transformation number 1. This is what does the heavy lifting when you don't know how else to proceed with penalties. We use this general procedure, transformation number 1, in lots of applications. And we'll come to see that there are applications where we can use transformation number 1 and number 2 in concert with one another, particularly in graph coloring problems, and I'll show you that in a moment as well. Okay. So if you think about this most general case, and one of the most famous problems of all in combinatorial optimization, the set partitioning problem, it's of exactly this general form, isn't it? In the set partitioning, we want to minimize CX, as shown there, subject to a bunch of equality constraints, as shown there. So we can apply, if we have a set partitioning problem that we want to solve, we can apply transformation number 1 straight away and convert that into a QUBO. Later on in the talk, I'm going to give you some computational results on set partitioning using this very transformation. We've done a lot of testing on QUBO applied to set partitioning. Graph coloring problems, obviously important problems in the combinatorial optimization field. Really thinking about this as a satisfiability problem. Can we find assignments of colors to edges in a graph such that to nodes in the graph, such that each node gets a color and such that adjacent nodes have different colors, okay? So if you think about the first concern, making sure that each node, each vertex gets a color, that's a bunch of assignment constraints as is shown there in the middle of this slide. So we've got 0, 1 decision variables denoting whether or not a given color is assigned to a given node. And we have constraints that make sure, a constraint for each node in the graph to make sure that that node does in fact get a color. And for our second concern that, adjacent vertices must have different colors, well, that's what we talked about earlier, isn't it? That special constraint that we referred to as transformation number 2, and we formulate them as is shown at the bottom of the slide there, saying that adjacent vertices in the graph cannot have the same color. So we have these two sets of constraints for graph coloring. We have these color assignment constraints to the nodes, to the vertices, and then we have these adjacency considerations. So to build a QUBO model for a graph coloring problem, we can use the quadratic penalties from transformation number 1 on our first set of concerns, our assignment constraints, and then we can use transformation number 2 on our adjacency constraints, okay? We have a lot of experience with these types of problems. Have written a couple of articles on this and have another article in the works right now extending some of these results, okay? So here would be a little example of a graph coloring problem where we have this graph with these 5 vertices, and we want to color it with 3 colors, find a feasible coloring with 3 colors. So what that boils down to is the system of equations as shown there. We have a color assignment constraint for each of our 5 nodes, and we have these adjacency considerations as well. Applying, and I know this is a little hard to read, applying transformation number 1 and transformation number 2 in concert on this, you get the QUBO model X transpose QX, where this is what the Q matrix looks like. And that again is a small QUBO, easy to solve, and gives the optimal solution straight away. Okay. Well, what about a more general case, a general 0-1 linear optimization problem? As I comment here, as Fred and I put this together, many important problems in industry and government can be modeled as 0-1 optimization problems, but often they start out having a mixture of constraints. They don't all start out like AX equal B. They might have some less than or equal to constraints, some greater than or equal to constraints, and so forth. Well, we can always easily add slack variables, and we can represent our slack variables in terms of binary variables to create a system as shown here, max CX subject to AX equal to B. So provided that we add our slack variables, we can construct this problem in this more general form that we want, and then we can just apply transformation number 1. I want to give you an explicit example of that. So to do that, let's consider this little problem in 5, 0, 1 variables and 3 constraints. Note that the first constraint and the third constraint are inequalities, okay? So to convert my constraint set here into the form of AX equal B, I'm going to add slack variables for both of my constraints that are inequalities, slack and surplus if you like. Now to do this, what you have to do is estimate an upper bound on your slack activity, okay? And you use your domain knowledge to do that, okay? So for the first constraint, I'm going to say I don't think that slack activity is going to be any larger than 3. And for the second one, I say I don't think it's going to be any larger than 6. Now, where the heck did you get the numbers? Well, I just looked at the problem, thought about it a little bit, and went out on a limb and took a chance, okay? The worst thing that can happen to you is you underestimate that. And that's not necessarily so bad. You can recover from that, yeah. So since all our variables in our QUBO models are 0, 1 variables, I have to represent those slack activities in a binary expansion. So for slack number 1, for which I want to be between 0 and 3, I'm going to represent that by 1x6 plus 2x7. And likewise for slack number 2, okay? So converting my constraints into this system AX equal B, I can then build my QUBO model. I get my model X transpose QX. This is what the Q matrix looks like for that transformation. That model can be solved straight away. And we get that the original objective function is equal to 16, which is the optimal solution to the problem. Remember, when you do the general transformation, what we call transformation number 1, your QUBO model turns out to be X transpose QX plus an additive constant, okay? You have to come to settle up with that additive constant after the fact, yeah. Well, what if you start with a problem that's quadratic from the outset? Well, that often happens. We have these quadratic knapsack problems as an example of that, and we can proceed in exactly the same way. So if we have a quadratic knapsack problem as is depicted here, we just convert the constraint into an equality, put that quadratic penalty into the objective function as we normally do, and get a QUBO model straight away using, again, transformation number 1. So here's a little example of a quadratic knapsack problem where we start out with a knapsack of size 16. We add a couple of slack variables, and we build our QUBO model as is shown there on the bottom of this slide. Rewrite that as X transpose QX. For this particular model, notice you get a totally dense Q matrix here. Can solve this model and get the optimal solution to the quadratic knapsack problem. Again, we've done quite a bit of testing with knapsack problems, both single and multiple knapsack problems, and have a paper or 2 on that as well. Well, you might be thinking, yeah, but you guys are just showing us small examples, you know. Give me the real stuff, okay? Problems are big out there, yeah. Well, we've been doing some testing on some large problems, and what we want to show now is some results we've been getting on three different classes of problems: some set partitioning problems, some maximum diversity problems, and some large max cut problems, some deregular on deregular graphs. Okay, so I first want to take up the some results we've been getting on some set partitioning models. Okay, in the results I'm going to show, we have three different categories of problem instances. Some are of medium size, some are large, and some are very large. And just to give you a benchmark, we also solve these problems with Cplex. We applied a popular quantum computer solver as well. And then the solver that we have that from our company, NGQ, is a metaheuristic QUBO solver that we used also on these set partitioning problems. So for each of these test instances we're going to go through, we're going to show three different results, one from Cplex, one from a quantum computer, and one from our metaheuristic solver as well. So in this first slide, these problems are medium size. They have 6,000 variables, 6,000 binary variables. And there's just 8 of these problems. Cplex, all the solvers were given 5 hours to work on these. Notice that for 7 out of the 6 problems, Cplex had no trouble finding the optimal solution. On the last one, it came up a little bit short. In the middle, you see the results we got from a quantum computer. The quantum computer found pretty good solutions, but was unable to find the optimal solution for any of these problems. And on the right-hand side, we have our metaheuristic solver that quickly found optimal solutions to all of these problems. Now, these are medium-sized problems in set partitioning arenas, 6,000 variables. Yeah, oh yeah, thanks, Fred. I'm in such a hurry here. This is why you have a partner. Besides that, he's full of good ideas. Notice the difference in times. These are times to best solution. And notice the metaheuristic on the right-hand side is very quickly found really good solution, not only really good, found the best solutions known. In fact, these are all optimal solutions for these particular problems very, very quickly. Okay. Now I want to go to some larger problems. These have 10,000 up to 40,000 variables, and they're of various densities. So these are fairly dense problems for set partitioning problems. And again, we highlight in yellow the performance of the best performance for each problem instance in terms of objective function quality and the time at which that best solution was in fact found. Now these are larger problems. They're taking a little more time. Cplex was able to do well on about half the problems. The quantum computer had very erratic performance on these problems as shown there in the middle. In some cases returned results that were somewhere in the ballpark, but in other cases not. Our metaheuristic solver on the right-hand side found best known solutions fairly quickly. These times are all in seconds. We found with our metaheuristic solver high quality solutions very, very quickly as shown there. Now I want to show you some really large problems. At least we think they're large, from 50,000 variables up to 100,000 variables, 10,000 constraints up to 20,000 constraints as shown there. For these very large problems, we left the quantum computer out on the sidelines. It just couldn't perform. Notice that the metaheuristic solver, NGQ, found, and I'm not sure, we haven't proven the optimality of these solutions, but found best known solutions to these problems very quickly. CPLEX did a pretty darn good job, but did not match our metaheuristic solutions in a 5-hour period. Okay. So we solved in these tests problems going from 6,000 up to 100,000 variables. And again, this illustrates at least a couple of things. One is that the QUBO model in and of itself is capable of delivering high quality solutions if you have the right solver for the QUBO model. And it also illustrates that the particular metaheuristic solver that we have works very, very well on these types of problems. It calls into question, with the current state of technology, the capability of the quantum solvers right now on these very large combinatorial instances. Okay. I want to spend a few minutes on the max diversity problem. This is the problem that I think most of you know about. This is the formulation as shown here. It starts out in the form of a quadratic objective function and has a single cardinality constraint. So it's an easy model to easy problem to model, but it's a tough problem to solve. In the testing that we've carried out, we went to the MDL lab. There's a repository of test problems for the max diversity problems, and we picked out of that repository some of the large instances. And to give you a benchmark, we compared our performance with that of one of the state-of-the-art solvers. It's called OBMS. Okay. So in this case, from the repository, we found test instances to work on that were of 3,000 variables, but had different values for the cardinality right-hand side, as shown there. So n is the number of variables. They're all 3,000. M is the right-hand side of the cardinality constraint. And for a given size problem, like 3,000 variables and the cardinality right-hand side of 300, we have different instances that were randomly generated. Okay, and what we show there is that if you go over to the right, we show the results that were obtained by the state-of-the-art solver, and to the right of that, we show that we got exactly the same results. So I'm assuming, but I have no proof that those are the optimal results, but we get the same result that the state-of-the-art solver got. And notice the times, the right two most columns on the right-hand side. The state-of-the-art solver is a little more uniform in its time, but our heuristic was able to find the same solutions, and in many cases, much, much quicker than the state-of-the-art solver as well. Okay. So far we've seen some large set partitioning problems. We've seen some max diversity problems. And in each case, we've seen that the QUBO model is capable, with using an appropriate solver, to deliver really high quality solutions, best known solutions in many, many cases. And the last case has to do with the max cut, solving the max cut problems for some deregular graphs. And in this case, we're looking at some graphs of d equal 3 and d equal 5. And we get into some really large graphs here, okay? And yeah, I think you can read that reasonably well. So at the top of the graph, we have some results for the d equal 3 case, and the bottom of the graph for d equal 5. Notice that we go from 1,000 variables up to 1,000,000 variables in both cases. And what's plotted there in the graph are the approximation ratios. It's possible for these graphs to estimate an upper bound on the cut. And so what's plotted there is the ratio of what we got to that theoretical upper bound. Okay? And you notice the green line there, those are the approximation ratios we get for the d equal 3 case, and they're in the high 90%. Yeah. And likewise, the blue there is for the d equal 5 case. In the literature, people report things like 0.92, and our ratios are much higher than that. Okay, so we're getting very good results on some extremely large QUBOs. Now these are pretty sparse QUBO models. The Q matrices are pretty sparse. But these are the largest ones we've seen reported in the literature. Okay, QUBOs of size 1 million. Okay. So what those three examples of three different problem classes was intended to illustrate, again, was the viability of the QUBO model and the performance of meta-heuristic solvers like the one that we have in entanglement. Now, I want to highlight some things we're doing that move beyond the pure QUBOs. And these are extensions of the QUBO model that we refer to as QUBO plus models. And these are models that, for which we've withheld one or more constraints from the QUBO, from the Q matrix, and enforced them separately. So some of the more prominent QUBO plus models that we're working on are QUBO models that have a cardinality constraint, have assignment constraints, and have knapsack constraints. So these would be models that have a QUBO-like objective function, but have one or more classically formulated constraints that are solved with special extensions of our QUBO solvers. What we found computationally is that there are advantages in many applications of viewing your model as a QUBO plus rather than a pure QUBO. It's always possible to convert a QUBO plus model into a QUBO, a pure QUBO. But we find some computational advantage of keeping some key constraints outside of the Q matrix. If you think about things like portfolio models, one of the examples we ran into that really highlighted to us the computational advantage of QUBO plus was in the arena of portfolio models, where we wanted to keep a cardinality constraint outside of the Q matrix representing the size of the portfolio. So you've got 1,000 assets to consider, find the best portfolio that has exactly 10 assets. So that's a cardinality constraint that you could fold into the objective function, or you can keep it separate. Assignment constraints, we've done a lot of work on clique partitioning problems, and both as pure QUBOs and as QUBO plus models with assignment constraints, and likewise knapsack constraints. These are QUBO extensions for which we've extended our QUBO solver to enable really fast solutions to these problems. Some other things we're working on are what we call QUBO models. These are more general polynomial optimization models. So, of course, the QUBO model is the quadratic, but there are many, many important problems that are higher order polynomials, like, for instance, the max 3 set problem is naturally a cubic, okay? An unconstrained cubic model. So that, and we've done quite a bit of work on max 3 sat problems. And one way to proceed there is you can convert a cubic into a quadratic. But to do that, you have to introduce, in some cases, many, many additional binary variables. We've extended our quadratic solver to enable solutions to higher order polynomial problems, so we can solve them straight away without converting back to QUBOs. There seems to be, in many problem instances, an advantage to doing that, solving them straight away. Okay. Well, we got a variety of projects underway at our research group, and Vertex bisection. This is a list of problems we're currently working on. Importantly, we're working on advanced pre-processing procedures for quadratic problems, and you can see this list. We're working on some really interesting problems. It's really fun to think about new ways of formulating and solving problems, And that's what we've been doing for some time now. So I want to wrap up this part, and then we can see if you have any questions or comments. So what we tried to do today was to illustrate with some explicit examples of how to construct these QUBO models, talk about what they are, how to construct them, and give you some idea of the types of problems you might use a QUBO model on. Okay. I think we've demonstrated that the QUBO model is capable of delivering high-quality solutions to really important problems and large-scale problems. Okay, you know. And the large-scale success we're having is on the conventional side, not the quantum side. The quantum computing community, none of us know for sure what the future holds. It may be amazingly successful, but right now, they're not solving large problems like we are on the conventional side. Okay. I think it should be clear, at least we think it's clear, that as these solvers, both on the conventional and quantum side, continue to improve, there'll be more and more interest in this QUBO model as a representation of really important combinatorial problems. Okay. I want to highlight a couple of references if you're interested. This tutorial that we went over today appears in print, or actually the print version has more material in it. And we want to give a shout out to our friend Abraham Poonan's new book. There's a new book out on the QUBO problem if you're interested in learning more from the book. And I want to give a shout out to our colleague Udo, who helped Fred and I a lot on all of this. Yeah, yeah. Okay, we're open for questions.
Thank you for this tutorial. It's really great. I'm actually a statistician, so a lot of my problem turns out to be QUBO, like MaxiCat. So since I'm not well trained to solve the optimization problem, I wonder if you can comment on the solvers. Are there any differences, and how do you get those solvers to be able to solve those large problems? Thank you.
Thank you for the question. Yeah, it turns out that commercial solvers really don't exist right now. Now, let me qualify that. Gurobi has a solver now that will solve medium-sized problems. CPLEX does as well. The meta-heuristic solver that we use is proprietary to the company we work for. There are some solvers in the literature that have been available that are free. And I don't know if they're still available. Fred, do you know, or if there are solvers available on the, I know that you do you know of any? Yeah. Yeah, Gurobi works pretty darn well on, as long as your problem doesn't get too large. Yeah. And if you can send me an email, I'll have more time to think about it. If I have some I could recommend to you, I'd be happy to do that. Yeah.
Thanks for the talk. I also do some study on the QUBO and use the D-Wave machine to run case studies. And currently, my student, when my student run, is a free version. So the size of the qubit available is less than 600 qubit. And when I check online, the AWS can access the commercial D-Wave machine, and the commercial one, when I check, if I'm correct, is around 6,000 qubits. So here you mentioned that you can solve maybe more than 10,000 binary variables. At least when we to represent the variable, we at least need to use 1 qubit. And so could you explain more details about which quantum computer you use, and when you solve the problem, I say you definitely might decompose the problem. So what specific size of the machine you use so that we can get better information how you get the simulation result? Yeah, that's my question.
Thanks for the question. You know, I wish our third author, Rick Henning, was here. He's the one that actually solved these problems. For the very large instances, we use some resources from AWS, but I'm not sure exactly what the characteristics of those resources were. However, I have to say that Rick Henning, who's our software engineer that really developed our solver right now, the last version of it, he solved some sparse problems right on his laptop with up to 1 million variables. Yeah.
Just a quick, I was just wondering if some of the test instances that you solved are available like somewhere on a repository for other people testing.
The answer to that is I think so. Fred and I recently left the academic world and joined this company called Entanglement. It's a whole different world in the private world. So I think the answer is yes, but I have to check before I'd send them out to you. Yeah, but I'd be happy to do that if I'm able to. Yeah. Certainly the max diversity problems are public domain, and the R regular graph problems were randomly generated. I'm sure we could give you the, in that case, either the problems or the Python code to generate that. Yeah, just send me an email. We'll be happy to look into that.
Any other questions for? Right, and I'm sure they'll also be available after for Fenol, but you have a.
I have one more question. I have three students work on this topic, and we try different experiments. And one of the challenge we met is that the penalty, right? When we solve the, as you show here in the practical industry, we need to introduce the constraints, right? First, we need to actually add the penalty to convert the constraint problem to the unconstrained problem. So the penalty actually brings a lot of a challenge. So how do you set up the penalty will have a big impact on the performance of the solver? And I'm not sure whether you can comment on this. I believe it might be a commercial secret for your company. So I hope you can give us some information here. Yeah, thank you.
Thank you. That turns out to be a really good question. And I can comment to some extent on it. Yeah. You know, you think about the construction procedure where you have an original objective function and you create a new objective function that's now a combination of the original plus this penalty. And what you don't want is the penalty to overwhelm the information in your original objective function, okay? So you want that penalty to be large enough to do its job, and its job is to drive the infeasibilities to 0 for feasible solutions and have them positive for infeasible solutions. So you want that penalty to be large enough to do the job, but not too large to overwhelm the information in your original objective function. So it's kind of a balancing act and somewhat of an art rather than science right now. We usually get started by, we usually try and estimate the numerical value of the optimal value of the original objective function and use something for the penalty of that order of magnitude, okay? That's not a bad way to get started, but the proof's always in the pudding, yeah. The proof's in the pudding. You heard that here first. If you got nothing more out of this today, that you got that. Yeah, I mean, you got to check. If you're in doubt, you got to check. Now, another thing to mention is that, you know, what if you start with a problem that's infeasible? There's nothing magic about QUBO. It's going to give you a solution. You're going to construct it. You're going to get a Q matrix. You're going to get a QUBO model, and you're going to get a solution. Yeah. Proofs in the pudding.
Again, let's thank our speakers for this very informative talk. Thanks for being here, and then I'm sure they'll be able to entertain personal questions afterwards. So again, thank you very much.